Hypothesis testing, or significance testing, is one framework for making judgments in the face of noisy and imperfect data. But why might we need it in the first place? Aren't our own observations enough? Let's look at a toy example. It's contrived, but I promise you we're going to tie this back into science soon. Now, many games involve rolling dice, which introduce an element of chance. You don't know what number is going to come up next, unless you're cheating. One way to cheat is to use loaded dice, dice that are tampered with, so they're more likely to roll certain numbers. So this one here, this is a loaded die that I procured off the internet. And this is loaded, so it'll give you more sixes than usual. And I also have a fair die over here. So off camera, I rolled them each 10 times and wrote down the results. Let's look. Which one of these do you think is from the loaded die and which is from the fair die? Remember, I rolled them 10 times each. One row is from the loaded die and the other is from the fair die. What do you think? It turns out this row on the bottom is from the loaded die. Kind of tricky, huh? Okay, let's do it again. This is another set, 10 rolls from a loaded die and another 10 from the fair die. Which row is from the loaded die? Turns out it's this one. Did you get it? Okay, let's do it one more time. Which one is loaded and which one is fair? Turned out it was this one. It's actually pretty hard, right? Why is that? Well, one reason is that the loaded die can't be completely obvious if you want to get away with cheating. So if the dice were to roll a 6 like clockwork, that would be very easy to spot. So it's got to have a tendency to roll more 6s than usual, but it can't be so obvious because we would get kicked out of any game immediately. So loaded die of high quality are going to be subtle by design. It should be giving a 6 more often than usual, but not to an entirely obvious degree. Another reason is that spotting true randomness, like the fair die where every outcome is equally likely, is actually kind of hard. We know intellectually that lots of things in the world are noisy. They have an element of chance to them, is what I mean, but it can still be very hard to reason about in practice. So, for example, this roll just 3 4s in a row. Sometimes people find that awfully suspicious and say, how could that really happen from a fair die? But in fact, it's not that uncommon. So a string of a repeating number can happen, quite often by chance. Now, fairness or being loaded, is a property that happens over many, many, many rolls. So let's take a look at what this means. So what we're going to do is first, we're going to imagine what happened if we rolled our fair die many, many times, and we're going to use a computer to help us simulate this. So first, what I've done is I've taken, 10 of our rolls here and I've plotted them. So the number 1 came up 3 times total in the sequence. So in the bar graph, the number 1 is 3 high. We got a 1 3 times. We got a 2 only once. So the 2 has only a 1 high bar. 3 didn't come up at all. 4 came up a total of 5 times, so it's got a bar that is 5 high, etc. So this bar chart is just a different way of representing how often each number came up in our first 10 rolls of the die. Now we're going to use a computer to go up to 20 rolls. Okay, look at this. So we've still got some differences between the numbers. The 4 and the 6 came up the most. Now 50 rolls. Okay, so it's still kind of a jagged pattern. Not every number has come up equally often. When we go to 100 rolls, we can see, okay, it's starting to smooth out a little bit, right? So there's less differences between the numbers. So when we go to 1,000, it's getting even smoother, right? The differences between how often each number came up is even smaller. And here's 10,000. Okay, so this is quite a lot of dice rolls, more than you'd want to do by hand. And the differences in how often each number came up is really shrinking. And we can see, if we plot a line here, kind of in the middle of all these, we can see that the numbers are converging on being very similar. So, we don't see a very big disparity anymore between like a 4 and a 5. Now let's do the same thing with our loaded die. Okay, so our first 10 rolls are represented here. Here's the outcome of 20 rolls and 50. Okay, we're starting to see a bump around 6, 100, 1,000, and 10,000. So we're converging on a pattern where the 6 is quite overrepresented, and it looks like the 1 is sort of, at the 6 comes at the expense of the 1. It looks like this dice maker privileged the 6, and, that means that we'll get less 1s. And then 2, 3, 4, and 5 are all pretty similar. So let's see these two dice roll patterns side by side. This is 10,000 rolls with our fair and our loaded die. And so here's really, a representation of what it means for one of our die to be fair and one to be loaded. In the fair die, every number, every outcome has a roughly equal shot, right? It's not perfectly equal, but, as we get to a really high number of rolls, we're seeing very minimal differences between them. And with our loaded die, the more we roll it, the more a pattern emerges, that there is quite a marked chance of having a 6. So simply playing with 2 die, where I don't get to see anywhere close to infinitely many rolls, it might be hard to confirm with any confidence which is the fair one and which is loaded. Using only a couple rolls like 10 or 20, it would be easy to fool myself in either direction. Tools like significance testing or hypothesis testing help us put our observations into context of how much randomness we should expect as a baseline. Now, in the next video, we're going to walk through an example from beginning to end of how we might conduct such an investigation.